Let's discuss question number 32 from test 5. This is from thermodynamics, applied thermodynamics. So a gas turbine power operating at ideal Brayton cycle. So let's first draw what is ideal Brayton cycle. All the process are ideal processes. Okay, so ideal Brayton cycle, the best is to draw in a TS diagram. Okay, so if you start from here, so it's initially it's isentropic compression, so straight vertical line, and then it's constant pressure heating, and then it's isentropic work in the turbine, and then it's coming back in a heat rejection in the condenser. So 1 to 2 is isentropic compression, 2 to 3 is heating in combustion chamber, constant pressure. These are all constant. The 2 to 3 and the heat addition and the heat rejection are all constant pressure. 3 to 4 is work given in or isentropic work in turbine, and 4 to 1 is heat rejection is condenser. So now all these are ideal processes. Okay, and because air is the medium, so air we assume it's ideal gas, and for ideal gas the enthalpies, change in enthalpies is just related to change in temperature by this simple way. Okay, so now I need to just find out the temperatures, because once I get all the temperatures or all the points, I can easily just calculate the changes in enthalpies, and that will be nothing but the work required or the work. So what is asked is the net work. So from this I need to find out the work that is given out for the compressor that is required. So work output which comes in 3 to 4, but then some work is given to the compressor 2 to 1. So I need to find out the temperatures first at all the points, and then sequentially find out the changes in enthalpy and then relate it to the work. So first process 1 to 2 is isentropic, and isentropic is nothing but reversible adiabatic process. And so we have couple of equations. PV power gamma is constant, and then you have TV gamma S1 is equal to constant, and we also have that it's ideal gas, so PV is MRT. So if we apply these two, let's say apply this here, what I get is P T power gamma by P power gamma is equal to constant, and there is nothing but T power gamma by P power gamma is 1 is equal to constant. And if we can bring that side, so it is T by P gamma is 1 by gamma is equal to constant. So I can write T2 by T1 is P2 by P1, and this ratio gamma from this. Okay, so T2 by T1 by P2 by P1. Now T2 is something, so pressure ratio is something which we know. So this pressure by this pressure ratio is 8. So P2 by P1 is P3 by P4, that is 8. So this will be quite useful. So T2 and T1, the gas temperature, the compressor inlet is 300, so that is 300, and T2 is something which I need to find, this 8. Then gamma is 1.4, specific heat ratio Cp by Cv, so that is 8. So from this you will get easily T2, which is 543.43 Kelvin. So T2 I know. Now let's apply for 3 to 4 is also isentropic expansion. So 3 to 4, if I apply the same thing, it's isentropic expansion. So T3 by T4 is P3 by P4 gamma minus 1 by gamma. So P3 by P4 is 8, gamma minus 1 is 1.4, T3 something which I don't know. T4 is, so T3 is given, sorry, the T3 at the turbine inlet, that is the maximum temperature which comes from the material limitation, can't go beyond this, so I can find T4 now. So T4 will be 1300 by 8.4 by 1.4 to the power. So this value comes out to be 717.67 Kelvin. So now I got the temperatures, and now if I apply the steady flow work first law, so H2 minus H1 is the work input that is given to the compressor, and H2 minus H1 is Cp, T2 minus T1 because of the ideal gas assumption. So that is the work input, and so Cp is 1.005 for the air. T2 we already got 543.43 minus 300 is the temperature of the compressor inlet. So this value comes out to be 244.64. Remember we are doing for one unit mass, so it's kilojoules per kg because 1.005 is kilojoules. Now work given out by the turbine is nothing but difference in the enthalpies. Enthalpy decrease, so H3 minus H4. Velocities at the inlet outlet are very small, so neglected. That's why we don't have the velocity terms. T3 minus T4. Cp is 1.005. T3 is 1300. This is standard problem on Brayton cycle. 6-7 sets, and so this value comes out to be 585.25 kilojoules per kg. So this is how. Okay, so the net work is turbine minus what is required to run the compressor. So 585.25 minus 244.64. So this value comes out to be 340.6 kilojoules per kg. So 340.6 kilojoules per kg, close to 341. So the answer is C. Thank you.